Hi, my name is Christopher Padilla. This is video 5 for ME210, Kinetics of a Rigid Body. And today, the kinetics of a rigid body, we will be talking about a rail cart, specifically these that carry containers that are then moved along in intermodal facilities. Um, as you can see, they have four wheels that go on a track. Now, with this problem, we have our assumed, which is that with the wheels on the track, there is no slippage during the movement. Additionally, the cart is a rigid body despite it having um, a couple of different factors, including um, removable parts on the cart itself and then the boxes that go on top. We're just going to consider it all as one rigid body. And then additionally, we also have some static friction at wheels and track. Although there is very, very little friction within those surfaces, there is some to be accounted for in this problem. And as you can see in the diagram above, we have our center of gravity, h representing the height between the ground and the center line of the center of gravity. And then as you can see, we have some static friction along the wheels, not just on the front one, but on both. Continuing, we have our free body diagram. Um, to start off with, we have our coordinate system X and Y going in normal fashion. Additionally, we can continue with our weight that's being pulled down in the Y direction. Um, we have our normal forces that are pushing upwards in the Y direction as well. Despite this figure only showing 2 points, there's actually four, again, because there's four wheels. Now for the forces in the X, we have our static friction, and then we have our direction of motion towards the right. For inertia diagram, it becomes a lot more simple. Again, we have our center of gravity. We do not have anything going on in the y direction. However, in the x, we have our mass times acceleration in the x, depicting the movement uh, in this scenario. And then finally, we continue with our equations of motion, yellow being for the free body diagram, green being for the inertia diagram. So we start off with some of the forces in the free body diagram for the x being equal to 4 mu s times the normal force. 4 again being for the four wheels. The normal force, as you can see on the top, is equal to 0.25 times the weight. Weight being mass times gravity, but just shortening this here. And the 0.25 again to divide the total normal force by the four wheels. Uh, Again, for some of the forces in the inertial diagram, in the x direction, we have mass times acceleration in the x. Now, when we put these equations together for our equation of motion in the x, we have 4 mu s normal force is equal to mass times acceleration in the x. And then continuing forward, we have for our y direction, the free body diagram in the y is equal to 4 times the normal force minus the weight, as they go in opposite directions and they oppose and contradict each other. Um, Again, 4 because of the 4 wheels in the cart, that's self-explanatory at this point. And then for the inertia diagram, we actually have a value of 0 in the y direction. Again, as there is no movement or inertia to be made in the y direction. This is only going in the x. Finally, when you equate these, um, we're able to get a result of a resultant equation of motion equal to, well, total equation of motion is 4 times the static friction coefficient is equal, times 0.25 weight, and that is equal to mass and acceleration in the x. You can further simplify this by getting rid of the 4 and the 0.25, and you would get an even smaller equation of mu s times the weight is equal to mass and acceleration in the x.